Deep in the Carinae Nebula lies a star that defies death itself, Eta Carinae. It exploded not once but twice, and somehow it's still alive. How can a star survive its own destruction? Tonight, we'll explore one of the strangest objects in our galaxy. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, do you think Eta Carinae will explode again in our lifetime? Thank you for watching. Now let's begin. The Carinae Nebula stretches across a wide region of the Milky Way, a complex of glowing gas, dark dust and young stars that fills the field of view with structure at many scales. A nebula in this context is a cloud of gas and dust in space, dense enough to shine by its own emission or by reflected light from nearby stars. In the Carinae region, both processes are present. Cavities of ionized gas emit a soft glow where energetic radiation from hot massive stars strips electrons from atoms, while thicker dust lanes and cold clumps remain in shadow, silhouetted against the brighter background. The scene is patchy and broken with bright walls, dim recesses and narrow threads of material that twist and branch. Some zones appear almost empty, evacuated by powerful stellar winds, while other zones remain crowded and opaque, holding on to gas and dust against the pressure from their surroundings. Across this landscape, new generations of stars continue to form inside the denser pockets, drawing on the remaining reservoir of cold material. From a distance, the Carinae Nebula appears as a single object, but closer inspection reveals a network of distinct subregions. There are extended ridges where gas is compressed into long bright arcs and pillars that point inward toward the clusters of massive stars shaped by radiation streaming from those clusters. Broad faint shells mark where earlier episodes of star formation have pushed gas outward, leaving behind a more rarefied interior. The gas is mostly hydrogen with helium and trace amounts of heavier elements created by earlier generations of stars. Dust grains, tiny solid particles rich in carbon, oxygen, and silicates mix with the gas. Together, gas and dust govern how light travels through the nebula, sometimes scattering it, sometimes absorbing it, and re-radiating it at longer wavelengths. Invisible light, dark dust lanes, and bright emission filaments stand out. In infrared light, hidden young stars and warm dust become more prominent. In X-ray light, hot diffuse gas fills some of the cavities, a sign of earlier energetic events. The nebula evolves on astronomical timescales as radiation, gravity and gas pressure continually reshape it. Massive stars in the region emit intense ultraviolet light that ionizes gas and heats nearby material. This creates expanding regions of ionized hydrogen that glow with characteristic emission lines. At their edges, ionization fronts advance into surrounding molecular clouds, eroding them and compressing their surfaces. Where the compressed layers become dense enough, they can fragment into cores that collapse under their own gravity to form new stars. In this way, radiation from existing massive stars both erodes and stimulates star formation in nearby clouds. Stellar winds flows of charged particles streaming from stellar surfaces add another layer of influence. These winds carve bubbles in the gas ray's shells and stir turbulence. Over millions of years, the combined actions of radiation and winds from many massive stars transform an original molecular cloud into a complex of cavities, filaments, and leftover dense knots. Within the Carinae Nebula, the balance between destruction and creation is delicate. In some places, feedback from massive stars clears out gas so efficiently that it may halt star formation locally by removing the raw material. In other places, the same feedback compresses gas into new dense regions that are more likely to collapse, leading to a new generation of stars. Cold molecular clouds linger as irregular blocks and ridges, carbon monoxide and other molecules tracing their outlines. Along their surfaces, bright rims and thin interfaces mark where ionized gas pushes against neutral material. Deeper inside, far from the harshest radiation, dense cores and filaments retain conditions suitable for star formation. The process is not uniform in time or space. Some sectors appear older, dominated by cavities and clusters that have already done most of their clearing work. Others appear younger with more continuous cloud structures and fewer exposed clusters suggesting more recent or still ongoing collapse. Gravity plays a quiet but persistent role in this environment. It draws gas and dust into denser clumps, helps bind young clusters, and maintains the overall coherence of the larger complex despite the disruptive influence of radiation and winds. In regions where gas is sufficiently dense and cool, gravity can overcome thermal pressure and initiate collapse. When this happens, the cloud fragments into multiple cores, each likely to form one or more stars. The most massive of these new stars rapidly become significant sources of ultraviolet light and stellar wind themselves. They join the existing population of massive stars and begin to influence their surroundings in turn. Over tens of millions of years, this cycle gradually disperses the original cloud, leaving behind clusters of stars and a more diffuse interstellar medium. Observations across many wavelengths support this layered view of the Carinae region. Spectroscopy, the study of how light is spread into its component colors, measures velocities and physical conditions of the gas. Emission line profiles reveal expansion motions in some shells and turbulent motions in others. Line ratios indicate temperatures, densities, and ionization states. Infrared surveys map dust temperature and column density, highlighting where material remains cold and dense. X-ray observations show where hot plasma fills interiors of cavities, likely heated by shocks from winds and past explosions. Radio observations trace cold molecular gas. Together, these data outline a three-dimensional structure in which hot ionized interior regions sit alongside cooler, denser clouds, all embedded in a larger galactic environment. The stellar population in the Carinae Nebula spans a wide range of masses and ages. There are clusters rich in very massive hot stars that emit most of the ionizing radiation in the region, and numerous lower mass stars in various stages of early evolution, still surrounded by disks or envelopes of gas and dust. Many of these young stars are revealed as point sources in infrared images, where their warm circumstellar material stands out against the cooler background. Some drive jets and outflows that can be traced in emission lines, adding small-scale features to the larger pattern of flows and shocks. The presence of both very massive short-lived stars and more slowly evolving lower-mass stars indicates that star formation has been active in Carinae over an extended period. The most massive stars end their lives after only a few million years, while lower-mass stars remain on the main sequence for much longer. This mixture shapes the evolution of the region and sets the scene for the behavior of the most luminous and unstable members embedded within the nebula. Radiation from massive stars in the Carinae region spreads outward through space and meets the surrounding gas and dust, where it changes both the temperature and the state of the material. The most energetic light is in the ultraviolet part of the spectrum, which has enough energy to remove electrons from atoms and create ionized gas. When an atom becomes ionized, it gains a positive charge, and when electrons later recombine with ions, they emit light at specific colors. These emission lines give the bright parts of the nebula their characteristic glow. The ionized regions are hotter and lower in density than the cold molecular clouds around them, so they expand outward, pushing against neutral material. At the boundaries between ionized and neutral gas, thin layers form where the balance between pressure, radiation, and gravity is delicate. These layers are often where new shapes emerge in the nebula. Ionization fronts, which are moving surfaces where neutral gas becomes ionized, slowly eat into the cold clouds. As they advance, they compress the gas just ahead of them. If that gas becomes sufficiently compressed, gravity can begin to dominate and cause parts of the layer to collapse into denser clumps. Over time, these clumps may become the seeds of new stars. The same radiation that erodes clouds can therefore also help to trigger star formation in their outer layers. In regions where the radiation is strongest, gas and dust are removed more quickly, exposing the denser interiors of clouds in sharper outline. The result is the familiar sight of dust pillars and sculpted ridges that point back toward the sources of radiation. A dust pillar is a narrow, elongated structure of relatively dense gas, and dust that remains after the surrounding lower density material has been stripped away. The head of the pillar facing the hot stars is continuously eroded by radiation and by particles flowing away from the stars. This process, sometimes called photoevaporation, causes gas to stream away from the surface of the pillar. At the same time, the pressure of the ionized gas around the pillar can compress its interior, favoring the formation of denser cores. This balance between erosion and compression gives pillars their internal structure, with pockets of gas that may ultimately collapse into stars while the outer layers gradually disperse. Stellar winds add another layer of influence. A stellar wind is a continuous outflow of charged particles from a star carrying momentum and energy into the surrounding medium. Massive stars in Carina have strong winds that can reach speeds of thousands of kilometers per second. When such a wind collides with the ambient gas, it drives a shock wave into the surrounding material, heating it and sweeping it into a shell. Over time, these winds carve out cavities around the stars, creating bubble-like regions of hot, low-density gas outlined by denser shells. In a crowded region like Carina, many such bubbles overlap and merge, producing a network of cavities and shells that interact with one another. Where winds from different stars collide, additional heating and compression can occur. The mechanical energy injected by winds over the lifetimes of massive stars maintains extended volumes of warm and hot gas and helps to support the nebula against its own gravity. The shapes seen in images of Carina, such as towering walls, columns with bright tips and tunnels of diminished emission, are the visible traces of these processes. In some places, arcs and ripples along the edges of clouds show where pressure waves move through the gas. In others, small isolated clumps known as globules survive inside cavities, their dense cores resisting erosion. These globules often have bright rims and may host very young stars deeply embedded within them. As radiation and winds strip away their outer layers, any embedded stars gradually become visible at optical and infrared wavelengths. The interplay between radiation, winds, and gravity is not static. As massive stars evolve, their luminosities and wind strengths change. New massive stars appear in regions where clouds have recently collapsed, while others age and end their lives. Each change adjusts the balance of pressures and the shapes of ionization fronts and shells. Over intervals of millions of years, this leads to cycles in which clouds are assembled, illuminated, eroded, and dispersed. Embedded within all of this, the wider Carina complex transitions through different phases of star formation activity. In an earlier stage, cold molecular gas may dominate with only a few young clusters, beginning to emit strong radiation. At a later stage, much of the cold gas has been ionized or removed, and the remaining material is concentrated into pillars, ridges, and isolated clumps. Observations of Carina suggest that both stages are present in different parts of the nebula at the same time, so a spatial snapshot reveals a sequence of evolution spread across the region. From the standpoint of physics, the sculpting of Carina can be described by equations of hydrodynamics and radiative transfer, but in this script it is enough to note that flows of gas respond to gradients in pressure, and that pressure is set by temperature and density. Ionized gas heated by ultraviolet radiation has higher pressure than adjacent neutral gas, so it tends to expand and push against cooler regions. Shocks driven by winds further raise pressures and densities in shells. Gravity acting inward tries to hold mass together. Where gas is too diffuse or too hot, gravity cannot cause collapse, and the material remains part of the diffuse nebula. Where gas becomes sufficiently dense and cool, gravity can take over and pull it into stars and clusters. Instruments sensitive to different wavelengths of light highlight different aspects of this interplay. In visible light, bright emission from ionized gas outlines, ionization fronts, and the surfaces of pillars. Dark lanes mark regions where dust blocks background light. Infrared images reveal the warm dust on the surfaces of clouds and the hidden interiors where young stars reside. X-ray observations show hot plasma filling bubbles created by winds and past energetic events. Each band adds information about temperatures, densities, and motions, helping to build a coherent picture of how radiation and winds sculpt the nebula. Through all of this, the Carinae region remains a laboratory, where the feedback from massive stars can be studied in detail, and the dust pillars, shells, and cavities that fill the scene at this stage define the structured environment through which gas dust and young stars continue to evolve. Within the Carinae Nebula, dense groupings of stars gather into clusters, and one of the most prominent of these hosts Eta Carinae among other very massive objects. A star cluster in this context is a gravitationally bound assembly of stars that form from the same parent cloud and roughly at the same time. The cluster around Eta Carinae sits within a carved-out cavity of the nebula, its hot stars pouring radiation and stellar winds into the surrounding gas. The stars are not evenly spaced. They crowd more tightly toward the center of the cluster and thin out toward the edges where they blend into the more general field population of the region. Among these stars, a subset stands out through their brightness and temperature. These are the very massive hot short-lived stars that dominate the energy budget of the cluster. They radiate strongly in ultraviolet light and drive powerful winds that reach speeds of thousands of kilometers per second. Their combined influence shapes the shared cavity of gas and dust and helps to keep parts of the volume free of dense clouds. Lower mass stars, far more numerous but much fainter, populate the same space and contribute to the gravitational mass of the cluster without dominating its radiation field. The cluster's origin lies in the collapse and fragmentation of a massive molecular cloud. Observations of similar regions suggest that such clouds can give birth to clusters containing thousands of stars within a few million years. In the Carinae region, evidence of past and present star formation indicates that collapsing filaments and cores have repeatedly produced new subclusters that then merge or interact. The cluster containing Eta Carinae likely forms in one of these episodes when a dense portion of the parent cloud becomes gravitationally unstable and breaks into many smaller condensations, each becoming one or a small group of stars. As these newly formed stars grow and ignite nuclear fusion in their cores, they begin to emit radiation and drive winds, gradually clearing out residual gas from the immediate area. Over time, the expelled gas reduces the overall gravitational binding of the system, and some stars drift outward or are lost to the wider field while others remain in a more tightly bound core. The result at the present time is a cluster that still contains massive stars and retains a recognizable central concentration embedded within a larger association of stars dispersed across the Carinae region. In the core of the cluster, the radiation field is intense. dust grains near the most luminous stars absorb ultraviolet and visible light and re-radiate it in the infrared. Spectroscopic observations reveal a range of stellar temperatures and luminosities from the hottest and most luminous blue stars to cooler, fainter stars, more similar to the Sun, and down to even lower mass stars that are difficult to detect at large distances. Massive stars show broad spectral lines associated with strong stellar winds and high temperatures, while lower mass stars show narrower lines and often signs of youth. Some stars in the cluster still retain disks of gas and dust, indicating that they are in early stages of evolution and may still be assembling mass or forming planetary systems. Others have already shed their natal material and appear as more isolated main sequence stars within the common cavity. The gravitational potential of the cluster helps to keep many of its stars together, despite gas loss and external tidal forces. Stars orbit within the cluster, their motions reflecting the total mass distribution. Over tens of millions of years, encounters between stars gradually redistribute energy, leading to processes such as mass segregation, where more massive stars tend to sink toward the center, while lower mass stars move to larger orbits. In the Eta Carinae cluster, some degree of mass segregation appears present with the most massive stars concentrated in the inner regions. This enhances their collective impact on the local environment, as their radiation and winds originate from a relatively compact volume. The central part of the cluster is therefore both the brightest and the most influential region in terms of feedback on surrounding gas. Eta Carinae itself resides within this context as one of the most extreme members. It is part of a massive binary system, but at this stage of the script the focus remains on its role as a luminous source within the cluster rather than on its immediate surroundings. Its light and wind contribute significantly to the ionization and mechanical energy budget of the cavity. Nearby massive stars add their own output, and together they create a composite radiation field that illuminates the surrounding nebula. This shared influence appears in the shapes and brightness of nearby gas structures, which often respond to the combined presence of multiple hot stars rather than to a single source. Shadowed regions where dense clouds block direct radiation from the cluster demonstrate the importance of geometry in shaping the appearance of the nebula, while brightly lit rims and arcs show where radiation has a clear path from the cluster core. Multi-wavelength observations of the cluster provide complementary views of its structure and contents. In optical images, the brightest massive stars dominate the scene, and the ionized gas around them glows with emission lines. In infrared images, many more stars become visible as dust extinction lessens and cool stars and warm dust come into view. X-ray observations reveal hot plasma produced by the colliding winds of massive stars, including contributions from Eta Carinae and its neighbors. Radio observations can detect remaining pockets of cold molecular gas and trace any ongoing star formation at the periphery. Together, these data sets show that the cluster is not a simple uniform group, but rather a structured system with subgroups and ongoing interactions between stars and gas. On larger scales, the cluster participates in the life cycle of the Carinae complex as a whole. Its massive stars, including Eta Carinae, inject energy and processed material into the interstellar medium through winds and later explosions. At the present stage, winds and radiation dominate, sculpting the immediate environment and supporting the expansion of surrounding shells and cavities. Over longer times, the most massive stars end their lives, their remnants adding compact objects, while their ejecta enrich the gas with heavier elements. The cluster gradually loses stars as they drift away under the influence of internal dynamics and external tidal fields, yet for now it remains a coherent luminous structure, nested within the wider Carinae Nebula, providing the local high-energy environment in which Eta Carinae and its neighbors continue to evolve. Within the wider cavity carved by the massive cluster, the space around Eta Carinae is not empty. It is filled with a sprawling field of knots, arcs, and filaments of gas and dust that extend well beyond the more compact central nebula. Astronomers refer to this ensemble as outer ejecta material that has been thrown out from the vicinity of the star system and now travels through the surrounding medium. These structures are irregular in shape and distribution. Some appear as isolated clumps, dense and bright in certain emission lines. Others form curved arcs or partial loops that trace segments of expanding shells. Thin filaments thread between and around these features, marking places where gas has been stretched or sheared. When mapped in detail, the outer ejecta cover a region several light-years across with complex three-dimensional structure. The velocities of these features measured from Doppler shifts in their emission lines span a wide range. Some knots move only modestly relative to the central system, while others race outward at hundreds or even more than 1,000 kilometers per second. The fastest pieces of ejecta carry significant kinetic energy and can drive shocks into the ambient gas. Where such shocks occur, gas is heated to high temperatures and emits in X-rays, adding a hot diffuse component that fills parts of the volume between denser clumps. The combination of hot-shocked gas and cooler, denser knots gives the outer ejecta a multi-phase character. Different phases coexist in close proximity, linked by ongoing interactions, as faster material overtakes slower material, and as all of it ploughs into the older surroundings of the Carinae Nebula. The chemical composition of the outer ejecta is not identical to that of the normal interstellar medium in Carinae. Spectra reveal enhanced abundances of elements such as nitrogen, relative to oxygen and carbon in many knots. This pattern indicates that the gas has been processed inside a massive star and then brought to the surface before ejection. In massive stellar interiors, nuclear reactions in certain layers convert carbon and oxygen into nitrogen. When mixing processes dredge this processed material upward, and winds or eruptions expel it, the resulting outflows carry a distinct chemical signature. The nitrogen-rich composition of many outer ejecta features therefore points to an origin in the outer layers of Eta Carinae's primary star at a time when internal mixing and mass loss were already advanced. Differences in composition among knots also suggest that ejecta may have been launched under slightly different conditions or from different layers. Morphologically, the outer ejecta do not form a simple, smooth shell around the star system. Instead, they trace a clumpy asymmetric pattern. Some regions show dense agglomerations of knots and arcs, while other directions are relatively sparse. In certain sectors, radial strings of clumps hint at directed outflows, perhaps shaped by the geometry of the central source, or by channels of lower density in the surrounding medium. Elsewhere, broken arcs suggest segments of larger shells that have been disrupted. The lack of perfect symmetry implies that the mass loss that created the outer ejecta was not uniform over the stellar surface or in time. As the ejecta expand, they encounter the pre-existing gas and dust in the Carinae region. This background medium is itself structured with cavities, filaments, and clouds left over from earlier activity. Where the expanding knots and arcs run into denser pockets of this material, shocks compress and heat the gas, and can cause additional small-scale structure. In some places, the outer ejecta sweep up ambient material into secondary shells. In others, they may be deflected or slowed, bending the original trajectories of individual knots. Over time, such interactions blur the record of the initial launch conditions, but careful measurements of velocities and positions can still reconstruct aspects of the outburst history. Imaging at high spatial resolution shows that many knots have internal substructure. Some contain bright cores surrounded by fainter envelopes, possibly indicating denser clumps embedded in less dense material. Others show bow-shaped fronts where motion through the surrounding gas creates a leading edge of compressed and heated material. Behind these fronts, tails of gas trail away, pointing back toward the central system and tracing the recent path of the knot. These details emphasize that each clump or filament is not static, but is evolving as it moves, cooling, fragmenting, and mixing with its environment. The outer ejecta also interact with the radiation field of Eta Carinae and the cluster. Ultraviolet light from the central region ionizes the surfaces of knots and filaments. As in the larger Carina Nebula, recombination of electrons and ions in these ionized skins produces emission lines that can be observed and used to diagnose densities and temperatures. The illuminated faces of knots facing the stars often appear brighter while their shadowed sides face away, sometimes hosting cooler, more neutral gas. Dust within the ejecta absorbs and scatters light, contributing to extinction along certain lines of sight. Infrared observations detect thermal emission from this dust, indicating that at least part of the outer ejecta carry substantial dust content alongside gas. The spatial distribution of dust within the ejecta affects how light from the central system and from other background sources is filtered and re-radiated. In some directions, dust-rich knots and filaments obscure portions of the inner regions, while in others, relatively clear paths allow more direct views. Kinematically, the outer ejecta preserve a record of multiple phases of mass loss from Eta Carinae over the past few centuries. By combining proper motion measurements, which track the motion of knots across the sky, with line-of-sight velocities from spectroscopy, astronomers can estimate three-dimensional velocities and trace back the approximate times when different groups of features were launched. This approach shows that the outer ejecta encompass material ejected at several distinct epochs. Inner regions tend to contain somewhat younger ejecta, while more distant knots often correspond to older episodes, though projection effects can complicate this simple picture. Regardless of the exact sequence, the present state is that of an extended expanding debris field around Eta Carinae, occupying part of the larger Carina cavity, yet distinct from the broader nebula structures further out. This debris field defines the immediate external environment through which radiation and winds from the central system now propagate and mediates the exchange of energy and material between the star system and the wider Carina Nebula. As attention moves inward from the scattered outer ejecta toward the central region around Eta Carinae, a more coherent structure begins to dominate the scene. This is the Homunculus Nebula, a bipolar cloud of gas and dust created in the 19th century Great Eruption of the system. The word bipolar here refers to the overall shape, which consists of two opposing lobes arranged along a common axis separated by a narrower waist. Each lobe resembles a hollow shell that is thicker in some places than in others, and the pair together outline a shape somewhat like two connected bubbles. The lobes expand outward from the central star system, carrying with them the imprint of the conditions at the time of ejection. In 3 dimensions, the geometry is not flat but volumetric, with curved walls, enclosing a central cavity in each lobe. The homunculus does not sit face-on to the line of sight from Earth. Instead, its main axis is tilted so that one lobe points somewhat toward the observer, while the other points somewhat away. This inclination means that the near lobe appears slightly brighter in some wavelengths, while the far lobe is more affected by dust. Measurements of Doppler shifts in spectral lines confirm this orientation, as one lobe shows gas moving toward the observer, while the other shows gas moving away. By combining these velocities with images of the expansion, astronomers can reconstruct the 3-dimensional layout and infer an ejection date that matches historical records of the Great Eruption. The lobes themselves are not solid. They are shells of gas and dust with a range of thickness and density. In some regions, the shell is comparatively thin, while in others it is thicker and more opaque. The interior of each lobe contains lower density material that contributes less to the overall emission and extinction. Infrared observations reveal substantial dust within the shells, which absorbs visible and ultraviolet light from the central system and re-radiates it as thermal emission at longer wavelengths. The distribution of this dust helps to shape the observed energy output from Eta Carinae and its immediate surroundings. In visible light, the surfaces of the lobes appear mottled with brighter patches where the geometry favours reflection or scattering of starlight, and darker regions where dust obscuration is strong. The overall outline, however, remains that of two opposing roughly symmetric lobes about a central point. The bulk motion of the lobes is predominantly radial away from the central stars. Typical expansion speeds in the main body of the lobes are of order many hundreds of kilometers per second, though exact values vary with latitude on the surface. Gas closer to the polar directions tends to move faster than gas near the waist, a pattern known as latitudinal variation in expansion velocity. This variation affects the final shape, making the lobes elongated along the axis rather than spherical. By fitting models of homologous expansion in which velocity is proportional to distance from the centre to observed positions and velocities, researchers infer that most of the mass in the homunculus was expelled over a relatively short interval during the 19th century event. In the present, the homunculus continues to expand its walls, moving steadily outward into the broader cavity, already influenced by earlier winds and outer ejecta. The mass contained in the homunculus is substantial. Estimates based on dust emission and gas traces suggest that several times the mass of the Sun have been expelled into these lobes. Removing this amount of mass from a massive star system in a short time alters the star's outer layers and its wind properties. Chemically, the gas in the homunculus shows signatures of nuclear processing similar to those seen in the outer ejecta, with enhanced nitrogen and depleted carbon and oxygen in many regions. This indicates that the expelled material originates from layers that have been mixed with products of hydrogen fusion in the stellar interior. Dust within the lobes likely forms from this enriched gas as it cools after ejection, producing grains whose compositions reflect the local chemistry. The presence of dust explains both the strong infrared output and the heavy extinction of light from the central system along some sight lines. The homunculus is not isolated from the radiation and winds that currently stream from Eta Carinae. Light from the central stars strikes the inner walls of the lobes, heating dust and driving photoevaporation of some gas. This process creates flows that move from the lobe surfaces into the interior cavities, adding a slower component to the overall motion. Some parts of the inner walls receive more intense radiation than others, leading to local differences in heating and ionization. Observations at different wavelengths and times reveal changes as the system moves through its orbital cycle. Despite this interaction, the large-scale structure of the lobes remains dominated by the original eruption dynamics. The surface of the homunculus displays a variety of textures in high-resolution images. There are smooth stretches where the shell appears relatively uniform, and regions where small-scale corrugations and ripples break up the surface. These patterns may arise from instabilities during or after the ejection, or from variations in the density of the expelled gas. In some places, faint striations follow lines on the lobe surface. In others, small protrusions or indentations mark spots where local conditions differed slightly from the surrounding regions. Together they show that the homunculus is a structured dynamic shell rather than a smooth envelope. The central waste region where the two lobes meet is narrower and denser than many other parts of the nebula. It forms a dividing zone between the two larger volumes and defines the point of closest approach of the expanding shells. This waste aligns roughly perpendicular to the main axis of the lobes and lies close to the plane in which much of the expelled material has lower velocities. Seen in projection, it partially obscures the far lobe and adds extinction along lines of sight that pass through it. The density distribution in this region influences how radiation from the central system escapes into different directions, and how the outward moving gas interacts with any remaining material from before the eruption. Even at the level of global form, the homunculus is a tilted bipolar expanding shell of gas and dust, with substantial mass and chemically processed material, defines a distinct inner zone around Eta Carinae, separating dense recent ejecta from the more diffuse outer ejecta and the larger Carina Nebula beyond. As the view focuses more closely on the Homunculus Nebula, attention turns to the polar regions of its bipolar lobes where the walls expand most rapidly, and the geometry of the eruption becomes clearer. The polar zones of each lobe extend along the main symmetry axis of the nebula, away from the narrow waist that separates the two sides. In these regions, the shell reaches its greatest distance from the central star system for a given age, because the gas there moves with higher velocities than gas at lower latitudes. Observations show that material near the poles travels at many hundreds of kilometers per second, with characteristic speeds larger than those measured closer to the equatorial plane. This gradient in velocity with latitude is a key feature of the homunculus and contributes to the stretched, elongated shape of the lobes. Instead of forming a nearly spherical shell, the expanding material assumes a form in which the polar caps push farthest outward, while intermediate latitudes lag behind, creating a continuous surface that is thicker and more extended along the axis. The term polar cap refers to the outermost part of a lobe near its tip where the shell curves around and closes. These caps are places where the expanding gas has swept up residual material in its path and where the density of the shell may be enhanced. High-resolution images reveal that the polar caps are not featureless. They contain mottled structure, shallow depressions, and small protrusions that hint at variations in the density and temperature of the gas and dust. Knots and clumps stand out against the smoother background, suggesting local inhomogeneities in the original outflow or in subsequent cooling and condensation. Thin striations may trace the flow of gas along the shell as it stretches and expands. Despite these details, the overall curvature of the polar caps remains well defined, and their positions and shapes provide strong constraints on models of the eruption. The expansion of the lobe walls, including the polar regions, follows a pattern close to homologous expansion, in which the distance of a parcel of gas from the center increases in proportion to its speed. Under this approximation, measuring the present-day velocities and distances of many points on the shell allows a back extrapolation to an origin time when the gas lies close to the star system. When researchers apply this method to the homunculus, they find an inferred ejection epoch that matches historical records of the Great Eruption in the 19th century. The polar caps with their large distances and high velocities play an important role in this reconstruction because they sample the fastest, most extended parts of the shell. The thickness of the lobe walls varies with latitude. Near the poles, the shell tends to be somewhat thicker in radial extent than at some intermediate latitudes, though the exact profile is complex. This thicker shell indicates that a substantial column of gas and dust is present along the line of sight, contributing to strong extinction and significant mass concentrated in the polar regions. Infrared observations show bright thermal emission from dust in these areas, consistent with grains heated by radiation from the central stars. At shorter wavelengths, the same regions can appear dark or heavily reddened because the dust absorbs and scatters visible light. The dual role of the polar caps as strong emitters in the infrared and strong absorbers in the optical underscores their importance in shaping the observed spectral energy distribution of the system. Because the homunculus is tilted relative to the observer, the near polar cap presents one aspect, while the far cap presents another. The near cap facing somewhat toward the line of sight suffers less extinction along the path to Earth, and often appears brighter in reflected and scattered light. Its motion includes a component toward the observer, leading to blue-shifted spectral lines. The far cap, oriented away, lies behind more of the dusty shell, and any additional foreground material making it more heavily obscured. Its motion includes a component away from the observer producing red-shifted lines. Comparing the brightness, colours and velocities of these two caps allows a determination of the three-dimensional orientation of the nebula and helps to link features seen in projection to their true locations in space. The polar zones also provide information about the energy distribution in the eruption. The high velocities there imply that a significant share of the kinetic energy of the outflow is directed along the axis. Estimates of the mass distribution with latitude derived from dust and gas measurements suggest that both mass and energy are concentrated toward intermediate and high latitudes, rather than being uniformly spread. Along the lobe walls between the waist and the poles, the density and velocity fields change gradually. Material at mid-latitudes has speeds between those of the equatorial and polar regions, and the shell thickness may vary in step. High-resolution spectroscopy across the lobe surface records line profiles that shift smoothly, with positions signaling a continuous flow rather than discrete rings or separated shells. This continuity supports a picture in which the Great Eruption expelled material over a relatively short interval in a pattern that varied with latitude but remained broadly coherent in time. Any smaller scale fluctuations in mass loss rate or velocity may be imprinted as local thickness variations or as fine structure on the surface, but the dominant effect is the global gradient that shapes the polar caps and walls. The interaction of the expanding lobe walls with the pre-existing medium is gentler in some directions than in others. Where earlier winds or outer ejecta have already cleared out low-density paths, the polar gas can move relatively unimpeded, maintaining higher velocities and a smoother shell. Where it encounters denser pockets of gas or dust shocks, may form at the outer boundary of the shell, causing local heating and compression. Such interactions can produce faint emission features just beyond the main homunculus boundary, or subtle distortions in the outer contour. Over the timescales since the 19th century, these effects remain limited, and the lobes largely retain the shape set at ejection, especially in the polar regions where the momentum of the outflow is greatest. Overall, the polar caps and expanding lobe walls of the homunculus define the outermost coherent structure in the immediate environment of Eta Carinae, recording the direction, speed and spatial distribution of mass loss during the Great Eruption, and marking the boundary between the dense bipolar shell and the more diffuse ejecta and cavity beyond. Around the narrow waist that separates the two polar lobes of the homunculus lies a flatter, more complex structure, often referred to as the equatorial skirt, a broad clumpy distribution of gas and dust that spreads outward roughly in the plane, perpendicular to the main axis of the nebula. This skirt does not form a single smooth ring. Instead, it is made up of arcs, knots, and irregular patches that share a general equatorial orientation but vary in density, thickness, and brightness. Some parts resemble short broken filaments that curve gently around the waist, while others appear as discrete condensations set slightly farther out. Together they create a mottled pattern around the central region, distinct from both the elongated polar lobes and the more distant outer ejecta. The equatorial skirt is important because it contains material that was expelled during the same Great Eruption that formed the main lobes but directed more into equatorial directions, adding a lateral component to the bipolar flow. Kinematic measurements show that gas in the skirt expands outward at speeds that are generally lower than those of the polar caps, yet still high enough to carry it steadily away from the central system. Typical velocities are of order a few hundred kilometers per second, with variations from feature to feature. These speeds place the skirt material at intermediate distances from Eta Carinae, compared with the faster polar gas and the slower, denser structures lying closer to the waist. When combined with estimates of distance from images, the velocities imply ejection times consistent with the 19th century event, reinforcing the conclusion that the skirt forms part of the same eruption-driven outflow pattern as the main lobes. The density distribution in the equatorial region is uneven. Some arcs and clumps are dense enough to be prominent in emission lines and in scattered light, while others are more diffuse and contribute mainly to extinction and faint reflection. Dust plays a central role here. Observations in the infrared show that the skirt contains substantial dust that absorbs radiation from the central stars and re-emits it as thermal emission. In optical images, this dust produces partial obscuration along lines of sight that pass through the equatorial plane, especially toward the far side of the nebula. Because the homunculus is tilted relative to the observer, the equatorial skirt does not appear as a perfectly symmetric feature in projection. Instead, some sectors look heavier or more extended than others, depending on the combination of true density variations and viewing geometry. Within the skirt, small-scale structure is abundant. Compact knots of gas and dust stand out against the more diffuse background, sometimes linked by thin bridges or filaments. These knots may represent local overdensities in the outflow where gas has cooled and condensed more efficiently, or where slight differences in the ejection velocity have led to collisions and compression. Some knots show bright rims on the sides facing the central stars where radiation heats and ionizes their surfaces, while their shadowed sides fade more gently into the surroundings. In scattered light, the equatorial structures can appear bluish relative to the redder emission from dust at longer wavelengths, reflecting the wavelength-dependent nature of scattering by small grains. Spectroscopic studies of the gas in the skirt reveal that its chemical composition is broadly similar to that of the lobes, with enhancements in nitrogen and depletions in carbon and oxygen relative to typical interstellar gas. This consistency supports the view that the skirt and lobes share a common origin in processed stellar material ejected from the outer layers of Eta Carinae's primary during the Great Eruption. Line profiles in spectra taken at different positions across the equatorial region show modest velocity gradients, indicating that the material flows outward roughly radially from the center rather than circulating in a bound ring. The absence of strong rotational signatures suggests that the skirt is not a stable, long-lived disk, but an expanding, dispersing component of the eruption. The interaction of the equatorial skirt with radiation and winds from the central system produces additional structure over time. Ultraviolet light from the stars ionizes surfaces of clumps and filaments, creating thin ionized skins that emit in characteristic spectral lines. Stellar winds streaming outward at high speed can sweep against the equatorial material, especially where the skirt lies within the path of these winds. In places, this may drive weak shocks into the skirt, compressing gas along leading edges and producing subtle arcs or bow-like features that point away from the center. Over the more than 1.5 centuries since the eruption, Such interactions have likely modified the original shapes of some equatorial features without erasing their basic outward motion. The equatorial region also acts as a partial screen for light from Eta Carinae when viewed along certain directions. Dust and gas in the skirt can obscure parts of the inner nebula and the central stars, especially for lines of sight passing through denser clumps. This leads to spatial variations in observed brightness and colour that depend on both the intrinsic emission and the distribution of intervening material. At infrared wavelengths, where dust opacity is lower, the skirt becomes more transparent and more of the inner structure is revealed. At shorter wavelengths, the same dust can cause deep attenuation, making the equatorial plane appear as a darker band or a region of complex patchy extinction. High-resolution imaging shows that the equatorial features connect smoothly in a geometric sense to the waist region of the lobes. The inner edge of the skirt lies close to the narrow central zone where the two lobes meet, and there is no sharp boundary between the bottom of a lobe and the beginning of equatorial material. Instead, the bipolar shell thickens and spreads into structures that extend more along the equatorial directions while thinning along paths leading toward higher latitudes. This continuity suggests that the same eruption produced both the elongated lobes and the flatter equatorial structures, with the outflow properties changing gradually with latitude rather than shifting abruptly between two distinct modes. In this sense, the skirt can be viewed as the equatorial extension of the homunculus containing a portion of the total eruptive mass, and playing a significant role in shaping how light and wind from Eta Carinae escape into the surrounding nebula. Inside the larger Homunculus Nebula, closer to the central star system, lies a smaller, fainter structure, often called the Little Homunculus, along with other inner shells and condensations that occupy the space between the main bipolar lobes and the immediate vicinity of Eta Carinae. The Little Homunculus is itself a bipolar nebula, but it is more compact and slower moving than the main homunculus. It is thought to have formed during a later outburst in the 1890s, when the system underwent a secondary episode of enhanced mass loss and brightness. This later event ejected additional material into the surrounding cavity, but with lower velocities and smaller total mass than the Great Eruption that produced the main lobes. As a result, the Little Homunculus remains nested well inside the larger structure, like a smaller set of lobes contained within a larger pair. Its presence adds an extra layer to the stratified environment around Eta Carinae, bridging the gap between the dense walls of the main homunculus and the more chaotic inner ejecta that lie still closer to the star system. The geometry of the Little Homunculus follows the same general axis as the main lobes, with two opposing components oriented along the established symmetry direction of the system. However, the shapes of these inner lobes are less regular and more affected by subsequent interactions with radiation and winds. Their expansion speeds are typically of order a few tens to perhaps a few hundred kilometers per second, significantly slower than the many hundreds of kilometers per second characteristic of the main lobe walls. Because of this lower speed, the Little Homunculus occupies a comparatively small volume, confined to a region only a fraction of the size of the main nebula. Spectroscopic measurements of velocities and positions support an ejection date around the late 19th century, consistent with the timing of the observed lesser brightening event. These kinematic signatures allow the Little Homunculus to be distinguished from both the older outer ejecta and the slightly younger or contemporaneous features nearer the star. The material that makes up the Little Homunculus shows chemical properties similar to those of the main homunculus, with evidence for nitrogen enrichment and altered carbon and oxygen abundances. This indicates that it too arises from processed stellar layers in the primary star. However, the lower total mass and smaller spatial extent mean that its contribution to the overall mass budget of the nebula is modest compared with the main lobes. Still, its location and velocity pattern provide valuable clues to the changing mass loss behavior of Eta Carinae across different episodes. The existence of a secondary bipolar shell suggests that the star system did not return immediately to a stable low-mass loss state after the Great Eruption, but instead experienced at least one further significant outburst. Morphologically, the little homunculus is more difficult to image directly than the main homunculus, because it is embedded in bright, crowded inner regions and partly obscured by dust. Observations often rely on spectroscopic mapping, in which emission and absorption lines are used to separate overlapping structures along the line of sight by their Doppler shifts. In some wavelengths, subtle arcs and small lobes appear superposed on the brighter background, and when interpreted together with velocity information, these features trace the inner bipolar structure. The shells of the little homunculus may be thinner and more fragmented than those of the main lobes, reflecting both the lower energy of the event and the stronger influence of later interactions with the central radiation and wind. Within the same general inner zone, additional shells and condensations surround the little homunculus. Some of these are slower-moving inner ejecta that appear as clumps filaments, or irregular patches between the inner bipolar lobes and the central star system. Their velocities are often lower than those of the little homunculus, and can include components both toward and away from the observer, forming a complex velocity field. These inner features may represent earlier wind material decelerated by interaction with newly ejected gas, or remnants of mass loss episodes that predate the Great Eruption but were overtaken and compressed by later flows. In other cases, they may be localized condensations that formed as gas cooled and compressed in the aftermath of the major events. The space between the little homunculus and the main homunculus is therefore not empty, but filled with nested structures and overlapping flows. Radiation from Eta Carinae and the cluster illuminates these inner shells and clumps. Ultraviolet photons ionize their surfaces, creating emission in lines of hydrogen, helium, and various heavier elements. In some directions, material associated with the little homunculus and inner shells lies directly in front of the central stars as seen from Earth, producing absorption features in the spectrum of the star system. These absorption lines reveal the presence velocities and column densities of gas along the line of sight, and provide information about how the inner ejecta are distributed. Variations in these features over time can indicate changes in ionization, state, or subtle motions of the gas. Dust within the inner shells and the little homunculus further modulates the observed light. Close to the star system, grains are exposed to intense radiation and may be heated to high temperatures, emitting in the infrared, and sometimes being destroyed or altered over time. In somewhat more shielded pockets, dust can survive longer, contributing to extinction and scattering of visible light. The resulting pattern of bright and dark patches combined with emission from ionized gas gives the inner region a complex layered appearance in high-resolution images. Kinematically, the little homunculus and associated inner shells occupy an intermediate position between the fast massive main lobes and the more recent stellar winds. By measuring their expansion velocities and current distances from the center, and by tracing their line profiles in different directions, astronomers build a timeline of mass loss. The arrival of the main homunculus marks the Great Eruption in the 1840s. The emergence of the little homunculus corresponds to the lesser outburst in the 1890s. Inner shells and condensations may record still finer variations in mass loss rate and outflow structure over the decades before and after these prominent events. Although uncertainties remain about the exact mass and geometry of each component, The presence of multiple nested shells indicates that Eta Carinae's mass loss history is not described by a single episode, but by a sequence of changes on timescales of decades. Dynamically, the inner shells and little homunculus respond to ongoing input from the central system. The current stellar wind from the primary and the wind from the massive companion expand into a volume already occupied by these earlier ejecta. In directions where the wind is strong and the inner shells are relatively thin, shocks can propagate into the older gas, heating it and altering its ionization. In directions where the inner shells are denser, they can slow or deflect the present-day wind shaping the flow. These interactions contribute to the complexity of the inner environment and set the conditions under which later phenomena such as the colliding wind region and associated high-energy emission operate. Even without yet examining those innermost zones, it is clear that the little homunculus and related inner shells form a distinct layer in the stratified structure around Eta Carinae, marking a later, slower, but still significant eruption, and adding to the cumulative record of how this unstable massive system has shed mass into its surroundings over the past 2 centuries. Closer to Eta Carinae than the nested bipolar shells of the homunculus and little homunculus lies a crowded volume of gas and dust often called the inner ejecta, where dense knots, jet-like structures and slower-moving material intermingle on small spatial scales. These features occupy the region between the inner shells and the present outflowing winds. Unlike the more coherent shells that define the larger nebulae, the inner ejecta form a patchwork of clumps, arcs, and filaments, whose positions and motions vary strongly from place to place. Some condensations are so compact and bright that they stand out as tiny nebulous patches in high-resolution images. Others appear as chains or short streams, aligned roughly radially away from the star system, giving them a jet-like appearance, even when their underlying geometry is that of strings of ejecta rather than narrow flows. Together, these structures show that recent mass loss in Eta Carinae is not limited to broad, smooth outbursts, but also involves localized parcels launched with a range of speeds and directions. The velocities of the inner ejecta are on average lower than those of the main homunculus lobes, yet they still reach fractions of the speed seen in the larger shell. Spectroscopic measurements reveal components moving at tens to a few hundreds of kilometers per second relative to the central system. Some bright knots show modest radial velocities but noticeable transverse motion, while others have larger line-of-sight velocities and align with more extended features that point outward. Slower knots can be overtaken and compressed by later, faster outflows, increasing their density and altering their emission properties. Dense clumps, in turn, can resist acceleration and remain distinct even as surrounding lower density gas is swept up or redirected. Chemically, the inner ejecta share the nitrogen-enhanced carbon and oxygen-depleted pattern, seen in the larger nebula, indicating origin in layers of the primary star that have experienced hydrogen burning and mixing. Emission line spectra from many knots show strong lines of nitrogen-bearing ions and other species that trace high densities and relatively low ionization states compared with the more diffuse gas further out. Some regions exhibit complex line profiles with multiple components reflecting overlapping flows or internal gradients within a single clump. In certain directions, inner ejecta lie directly between Eta Carinae and the observer, imprinting narrow absorption features on the stellar spectrum and revealing that some knots are extremely dense and partially shielded from the most intense radiation. Physical conditions in these condensations differ from those in the surrounding diffuse gas. Electron densities inferred from diagnostic line ratios can reach very high values, and temperatures vary with the balance between radiative heating, collisional cooling, and any local shock heating. In some knots, strong emission from low ionization species indicates gas that is partly shielded and exposed to a softer radiation field, while neighboring regions show higher ionization and more direct illumination. Dust mixed with the gas contributes both to extinction and to thermal emission at infrared wavelengths. Grains near the central system may be heated to high temperatures, yet in denser, better shielded cores they can survive for extended periods. The combination of dense gas and dust makes some inner knots effective local screens that cast shadows into more distant parts of the nebula, producing small-scale variations in ionization structure farther out. Among the inner ejecta, some features take the form of narrow elongated structures that stretch radially away from Eta Carinae. These strings or jet-like features have high length-to-width ratios and display velocity gradients along their extent. In many cases, velocities increase with distance from the central system, a pattern that may reflect accelerating outflow or the progressive clearing of a path through the surrounding medium. Their compositions and ionization states resemble those of other inner ejecta, supporting the idea that they are parts of the same general mass loss pattern, shaped into elongated forms by local dynamics and interactions. Where such structures encounter denser material in their path, shocks can form at their leading edges, heating gas and generating enhanced emission that appears as bright knots at their tips or slight bends, where the flow responds to variations in ambient density. The inner ejecta region is strongly stratified in ionization. Close to the central stars, hard ultraviolet and high-energy radiation can ionize gas to higher states, but dense clumps and dust columns restrict this radiation to limited solid angles. As a result, some zones remain in lower ionization states despite their proximity, while others become strongly ionized and emit in lines that require high-energy photons. This patchwork pattern changes over the orbital cycle of the binary system, as the relative positions of the stars and their winds alter the distribution of absorbing and emitting material. Observations spanning multiple cycles show that some knots vary in emission strength and ionization level on timescales of years, indicating that they respond to shifts in illumination and local conditions. Dynamically, the inner ejecta act as an interface between the historical shells and the ongoing mass loss. Present-day winds from the primary star and its massive companion expand into a volume already filled with dense clumps and slower gas. In directions where these winds encounter inner ejecta, shocks form, decelerating the wind and ablating portions of the dense material. Thin layers of shocked gas may envelop knots, raising their temperatures and altering their emission spectra. In other directions, where the volume is more tenuous, winds can expand more freely toward the walls of the little homunculus or the inner surfaces of the main homunculus. This uneven resistance shapes the flow, producing channels of easier passage and pockets where gas circulates or becomes confined. Over decades, these interactions gradually reshape the distribution of inner ejecta, though many dense knots endure as distinct entities. Because the inner ejecta sits so close to Eta Carinae, they play an important role in mediating how energy and processed material leave the star system and enter the larger nebula. They absorb re-radiate and scatter radiation from the stars, filter the hard photon field that reaches more distant gas, and provide obstacles and targets for ongoing winds. At the same time, they carry information about past mass loss episodes in their velocities, compositions and locations, forming a complex evolving layer that links the structured shells of the little homunculus and main homunculus with the still more compact zone further in. Closer to the central stars than the dense inner ejecta lies a region where outflowing stellar winds from the members of the Eta Carinae system meet and interact, forming a colliding wind zone shaped by the orbital motion of the binary. Eta Carinae is not a single star but a massive binary system with a very luminous primary star and a hot massive companion bound together in a highly elongated orbit. An elongated or eccentric orbit is one in which the distance between the stars changes significantly over the course of one revolution. In this system, the orbital period is about 5.5 years, and the separation between the stars ranges from relatively close at periastron, the point of closest approach, to much larger at apastron, the point of greatest separation. As the stars move along this orbit, each drives a stellar wind outward. The primary star launches a very dense, slower wind, while the companion drives a faster, thinner wind. Where these two flows meet, their pressures balance and form a curved interaction surface, with shocks on either side where the winds are abruptly decelerated and heated. The shape and location of this interaction zone are not fixed. They change with orbital phase as the distance between the stars and the orientation relative to the observer evolve. In a simplified picture, the denser wind pushes the contact surface closer to the companion, while the faster wind carves a cavity into the denser flow. The result is a three-dimensional structure that resembles a distorted cone or bow, wrapped around the star with the weaker wind momentum and trailing away from the system in a spiral-like pattern as the binary orbits. In reality, the geometry is more complex, but this conceptual framework captures the key roles of wind strength and orbital motion. The colliding wind region sits well inside the main homunculus and little homunculus shells, occupying a volume comparable in scale to the separation of the stars themselves. Its extent is tiny compared with the overall nebula, yet important in determining how energy and momentum from the current winds are deposited into the immediate surroundings. Gas in the winds starts out at high speed and relatively low density close to the stellar surfaces. As it flows outward, it carries kinetic energy and mass flux. When the opposing winds meet, strong shocks form where supersonic flows are forced to slow down. Across these shocks, gas is compressed, heated to high temperatures, and diverted sideways along the interaction front. On one side of the contact surface, post-shock gas originates in the primary wind, while on the other, it comes from the companion wind. The relative locations of these two shocked layers reflect the imbalance between the wind momenta. If one wind is much denser or faster, the contact surface lies closer to the star with the weaker wind momentum. As the stars progress along their eccentric orbit, the distance between them changes, altering the pre-shock densities and speeds at the collision point and shifting the entire interaction region closer in or farther out. Orbital motion also causes the colliding wind structure to swing and curve. At each instant, the winds flow roughly radially away from each star, but the stars themselves are moving around their common center of mass. This motion bends the interaction front into a spiral that trails downstream from the line connecting the stars. Close to the stars, the surface resembles a bow wrapped around the companion and opening away from the primary. Farther out, the spiral pattern becomes more pronounced as the winds carry the imprint of past orbital phases outward. Because the orbit is highly eccentric, conditions near periastron differ strongly from those near apastron. When the stars are far apart, the collision region sits at a relatively large distance from each star, where the winds have expanded and densities are lower. The interaction front is broad and the shocked gas can cool or expand depending on local conditions. As the stars move toward periastron, the separation shrinks, and the collision point moves into denser regions of each wind. The dynamic pressure of the flows increases and the curvature of the interaction surface changes. The cone of shocked gas can become more tightly wrapped around the companion and may be distorted by instabilities in the flow. In some phases, dense streams of primary wind can wrap around the companion and obscure parts of the colliding wind zone from certain lines of sight. The entire structure is therefore time-dependent over the 5.5-year orbital period. In addition to the large-scale shape, smaller-scale instabilities develop in the colliding wind region. When a dense, slower wind meets a faster, lighter flow, hydrodynamic instabilities can arise at the contact surface. These instabilities create ripples, clumps, and vortices in the shocked layers. Turbulence can develop as gas of different densities and velocities mixes. Radiative cooling, in which hot shocked gas loses energy by emitting radiation, influences the thickness and stability of the shocked zones. If the gas cools efficiently, it can condense into thinner, denser layers that are more prone to fragmentation. If cooling is less effective, the post-shock region remains hotter and more extended with smoother gradients in density and temperature. The colliding wind zone also interacts with the previously ejected material that fills the inner nebula. Although the winds collide primarily in the interior, the shocked gas and any downstream spiral wake flow outward and eventually encounter the slower inner ejecta. In directions where the path is relatively clear, the shocked gas can move outward and merge into the more diffuse interior of the nebula. In directions where dense knots or shells from earlier mass loss lie closer in the outflow, may hit these obstacles, driving secondary shocks and altering the local structure. Because the binary orbit is inclined to the line of sight, the orientation of the colliding wind cone relative to the observer changes over the orbital cycle. At some phases, the cavity carved into the primary wind by the companion may open partly toward the observer. At other phases, the dense primary wind can sweep across the line of sight and obscure the interaction zone. This changing geometry influences how emission and absorption from the colliding winds appear in the spectrum at different times, and it affects how radiation from the companion reaches more distant parts of the nebula. The colliding wind region in Eta Carinae is also a strong source of high-energy emission, because the shocks that form where the stellar winds meet heat gas to tens of millions of degrees Celsius. At such temperatures, the gas emits X-rays, a very energetic form of light. The brightness and spectrum of this X-ray emission change over the binary orbit, reflecting how the geometry and physical conditions in the shock zone vary with time. When the stars are well separated, the interaction front lies farther from each star, and the pre-shock winds have expanded to lower densities. The shocks that form under these conditions still heat gas to high temperatures, but the reduced densities limit the overall X-ray luminosity. As the stars move closer together on their eccentric orbit, the collision point shifts into denser parts of each wind. Stronger impacts between denser flows increase the emission measure of the hot gas, and the X-ray brightness rises. This gradual increase continues as the system approaches periastron, where the separation reaches its minimum and the wind collision becomes most intense. Close to periastron, additional effects become important. The dense primary wind can fold around the companion, and the colliding wind shock altering both the shape of the shock front and the line of sight through the system. In some phases near closest approach, portions of the hottest shocked gas may be hidden behind thick columns of absorbing material in the primary wind. This material preferentially absorbs softer X-rays, changing the observed spectrum. In extreme cases, the line of sight passes through so much dense wind that X-ray emission from the colliding wind region is strongly attenuated, leading to a pronounced dip or minimum in the observed flux. After periastron, as the stars move apart again, the geometry shifts once more, and the X-ray emission gradually recovers. This pattern of slow brightening, sharp decline near periastron and slower recovery repeats with each 5.5-year orbit. In the shock zone itself, the physics of gas heating and cooling determine the structure of the X-ray emitting region. When the supersonic winds from the primary and companion collide, their kinetic energy is converted into thermal energy behind the shocks. On the dense primary side, the post-shock gas can cool relatively quickly by radiation because the density is high. This cooling can cause the shocked primary wind to condense into a thin, dense layer wrapped along the contact surface. On the side of the fast thinner companion wind, the post-shock gas may remain hotter and more extended, forming a broader region of hot plasma that emits X-rays over a larger volume. The balance between these regimes depends on the mass loss rates and velocities of the winds, as well as on the separation between the stars at a given orbital phase. If the companion wind has a particularly high speed, the maximum shock temperature on that side can be especially high, and the X-ray spectrum extends to higher energies. Observations of the X-ray spectrum across the orbital cycle show changes in both total brightness and spectral hardness, the latter referring to the relative contribution of higher energy photons compared with lower energy ones. When the colliding wind region is relatively unobscured and the shocks are strong, the spectrum appears harder with more high-energy X-rays. When absorption along the line of sight increases, or when the shock structure becomes more complex near periastron, the observed spectrum can soften even if intrinsic changes in the shock still produce very hot gas. Beyond the central shock zone, some of the hot gas flows outward along the contact surface, cooling and mixing with other material as it travels. This downstream flow carries X-ray emitting plasma into regions where the density and radiation field differ from those near the stars. As the gas cools, its emission shifts to lower energies and eventually to longer wavelengths. The X-rays observed from Eta Carinae therefore arise not only from the immediate apex of the colliding wind region, but also from an extended volume of shock-heated gas that has been advected away from the collision point. However, the dominant contribution to the time-variable X-ray signal comes from the changing conditions in the inner interaction zone, because that is where densities, temperatures, and absorbing columns respond most sensitively to orbital motion. The colliding winds also influence emission at other wavelengths. Shock-heated gas emits ultraviolet and optical lines. In addition to X-rays, and variations in these lines can correlate with the X-ray cycle. Changes in line profiles and strengths over the 5.5-year period trace shifts in ionization and flow patterns near the colliding wind zone. As the companion moves in its orbit, the solid angle over which its radiation escapes into the surrounding nebula changes, partly regulated by the cavity carved by its wind and by the blocking effect of dense gas. When the cavity opens toward a particular direction, higher ionization states can appear in gas along that path. When the cavity closes or is obscured, those regions receive fewer high-energy photons and their ionization state declines. This directional modulation of radiation, combined with the intrinsic variability of the colliding wind shocks, means that the inner ejector and nearby nebula gas experience a changing high-energy environment over each orbital cycle. Observations spanning multiple cycles show that while the overall pattern of X-ray brightening and fading repeats, details can differ from one cycle to the next. Small changes in wind properties such as mass loss rates or speeds, or in the distribution of dense clumps in the inner ejector, can slightly alter the timing and depth of X-ray minima or the exact spectral shape at given phases. These differences indicate that the system itself is evolving on timescales of decades, even as the orbital period remains stable. Within the colliding wind region, any such gradual evolution is reflected in the shock structure, the temperatures and densities of the hot gas, and the degree of mixing between material from the two winds. In this way, the colliding wind shocks of Eta Carinae act as a current engine of high-energy emission, and as a sensitive probe of how the properties of the massive binary system change over time within a volume still enclosed by the larger, slower-moving shells and ejecta that record earlier stages of its history. The primary star in the Eta Carinae system is an extremely luminous, unstable object, whose outer layers do not form a sharp, well-defined surface, but instead blend into a dense stellar wind that carries mass away into space. A stellar photosphere is usually defined as the layer from which most of the visible light escapes. But in such a star, the photosphere becomes extended and fuzzy, because light emerges from within a thick, outflowing envelope rather than from a static surface. The primary star's luminosity is many millions of times that of the Sun, and its gravity must compete with the outward push of radiation on the gas in its outer layers. When radiation pressure becomes strong enough, it can lift material away from the star and launch a wind. In Eta Carinae's primary, this process operates on a grand scale. The wind is dense with large amounts of material flowing outward, and its speed reaches many hundreds of kilometers per second by the time it has accelerated far from the star. Close in very near the stellar surface, the gas moves more slowly and remains thick enough that photons scatter many times before escaping. In this region, conditions resemble those of an extended atmosphere, with a gradient in temperature and density rather than a sudden boundary. Farther out, the wind becomes more accelerated and dilute, but still dense compared with winds from many other hot stars. This continuous outflow shapes the star's spectrum and controls how its energy emerges at different wavelengths. In the deepest layers accessible to observation, the temperature remains very high, and atoms such as hydrogen and helium are ionized. As the gas flows outward and expands, it cools, and some ions recombine. Spectral lines seen in the light of Eta Carinae's primary arise in these outer zones, where different ions exist at different distances from the star. Broad emission lines of hydrogen and other species mark where recombination and collisional excitations occur in the moving gas. Because the wind has a range of velocities along the line of sight, with some material approaching and some receding, the lines are broadened by Doppler shifts. In some cases, characteristic profiles appear in which an emission component from the bulk of the outflow is paired with an absorption trough on the blue side produced by gas that lies between the star and the observer and moves outward. These profiles provide direct evidence that a massive wind is present and allow estimates of its speed and density. Modelling of the line, shapes and strength suggests that the wind is not smooth but clumped, meaning that gas collects in denser pockets separated by lower density regions. The mechanism that accelerates the wind involves absorption and scattering of photons in many spectral lines of heavy elements. In very luminous hot stars, the outward momentum carried by radiation can be transferred to the gas through these lines, pushing it outward. When the star's luminosity approaches a critical level, radiation pressure becomes strong enough to overcome gravity in the outer layers and drive a powerful wind. Eta Carinae's primary is thought to lie near or above this limit in its outer envelope, which helps explain the exceptional density of its outflow. Under such conditions, small changes in luminosity or opacity can lead to large changes in the mass loss rate. This sensitivity is one reason why luminous blue variables display episodes of enhanced mass loss and brightness changes. In the case of Eta Carinae, the 19th century, Great Eruption represents an extreme example, but even in its current state the star's wind remains heavy and variable. The outer wind also mediates how the primary star's radiation reaches the surrounding nebula. Light emitted near the stellar core must pass through the expanding envelope, where it can be absorbed, scattered, and reprocessed. In directions where the wind is densest, photons may be scattered many times, emerging at different wavelengths or directions than they had initially. In less dense directions, radiation can escape more directly. This angular dependence means that the primary's output is not necessarily the same in all directions. Density variations due to clumping or large-scale flows can create preferred channels through which radiation escapes. The wind also affects the spectrum by producing a background of emission from ionized gas, in addition to the stellar continuum altering the apparent temperature inferred from observations. Temperature in the wind decreases with distance from the stellar core because the gas expands and radiates energy away, though local shocks and radiative heating can modify this trend. Close to the star, heating by the intense radiation field dominates. Farther out, expansion and cooling cause the gas to become cooler and more rarefied. At certain radii, conditions may favor the formation of dust grains in the outflow, though in Eta Carinae the harsh radiation field near the star can destroy or inhibit dust formation very close in. Dust that does form at larger distances contributes to infrared emission and to the extinction of light from the inner regions when viewed through the wind. The density structure of the wind follows from the requirement that mass be conserved as gas flows outward. For a steady outflow, the mass passing through a spherical shell around the star must be the same at all radii. This implies that once the wind speed has reached a roughly constant value, the density decreases approximately as the inverse square of distance modulated by clumping. Where the wind speed is still increasing, the density falls more slowly with radius. Superposed on this smooth trend, clumps and large-scale structures produce local enhancements and deficits. These variations, combined with the radial changes in temperature and ionization, give the wind a layered character with distinct zones where particular ions dominate and where certain spectral lines form. Because Eta Carinae's primary is so luminous and unstable, its outer layers are expected to change over time as internal structure evolves and as energy transport responds to accumulated mass loss. Even modest shifts in temperature or luminosity can alter the balance between gravity and radiation pressure and thus affect the wind. At the present stage, the primary star is surrounded by a dense extended radiation-driven wind whose photospheric region merges gradually into the outflow and whose properties govern how the star's energy output couples to the surrounding little homunculus inner ejecta and larger Homunculus Nebula beyond, while remaining distinct from the companion's faster, thinner wind that interacts with it in the colliding wind zone. The secondary star in the Eta Carinae system is a hot massive companion whose radiation field and fast stellar wind add a distinct influence to the inner environment, different from that of the dense, slower wind of the primary. While many details of this companion remain uncertain because it is difficult to observe directly through the bright and variable emission of the primary and surrounding nebula, the properties inferred from spectra and from the behavior of the colliding wind region point to a star with a very high surface temperature and substantial luminosity. Its temperature is likely tens of thousands of degrees Celsius, high enough to emit strongly infrared ultraviolet light that can ionize atoms to higher states than the radiation from the primary alone. The mass of the companion is estimated to be on the order of several tens of times the mass of the Sun, and its luminosity is large, though probably less than that of the primary. Despite this, its harder spectrum means that in some directions it can dominate the ionization of certain species in the surrounding gas. Like the primary, the companion star drives a stellar wind, but the character of this wind differs. It is faster and less dense, with flow speeds of several thousand kilometers per second, and a lower mass loss rate than the primary's wind. As this fast wind expands, it carves out a cavity in the denser outflow from the primary, particularly on the side facing the companion. The boundary between the two winds is shaped by the balance of their momenta, and the resulting cavity provides pathways through which the companion's hard radiation can escape more freely into space. In directions where the primary wind remains dense and intact, that radiation is more strongly absorbed or scattered. Thus, even though the two stars share the same central region, the distribution of gas around them means that the companion's influence varies significantly with direction. The orbital motion of the binary system further modulates this pattern. As the stars move along their highly eccentric 5.5-year orbit, the separation between them changes, and the cavity created by the companion's wind evolves in shape and size. Near a pastron, when the stars are far apart, the cavity can open over a wider solid angle, and more of the surrounding gas sees the companion's hard radiation directly. Near peristron, when the stars come closer together, the dense primary wind can wrap more tightly around the companion, and its wind narrowing the channels through which high-energy photons escape. In some phases, dense gas in the primary wind may lie directly between the companion and particular portions of the inner ejecta, or nebula, reducing the ionizing flux that reaches those regions. In other phases, the line from the companion to those regions may pass through lower density zones, allowing more intense illumination. This changing geometry helps explain why certain emission lines that require high ionization energy strengthen and weaken over the orbital cycle in different parts of the nebula. The companion's radiation field creates zones of high ionization in the inner ejecta and the inner surfaces of the surrounding shells. In directions where the path is relatively clear, gas can show ions of helium and metals that need very energetic photons to form. When the companion is hidden, or its radiation is blocked by dense wind or clumps, those ions can recombine to lower states. Observations of these changes in ionization provide indirect evidence for the companion's presence and properties, even when the star itself is not directly visible in images. The pattern of high ionization features mapped across the inner region and monitored over time outlines the paths along which the companion's light travels and the structures that obstruct it. This makes the companion both a powerful source of radiation and a diagnostic probe of the three-dimensional distribution of gas and dust around Eta Carinae. The fast wind from the companion also contributes mechanically to the inner environment. Where it interacts with the denser primary wind, it shapes the colliding wind region, but beyond the immediate collision zone, the post-shock companion wind can flow outward along the contact surface, carrying energy and momentum into the inner nebula. In directions not blocked by dense ejecta, this hot gas can expand outward until it encounters the slower inner shells, or clumps in the inner ejecta. These encounters can drive secondary shocks and produce localized heating. Even though the total mass in the companion wind is smaller than in the primary wind, its high speed means that it still carries significant kinetic energy, making it an important contributor to the high-energy phenomena observed near the star system. The spectral signature of the companion is partly visible in the combined light of Eta Carinae, especially at phases when its contribution is less obscured. Certain absorption and emission features in the ultraviolet and optical ranges hint at a hot luminous star with a wind characteristic of early-type massive stars. However, the complexity of the surrounding environment, including the bright emission from the primary wind and from illuminated nebula gas, makes it challenging to isolate the companion's intrinsic spectrum. Models that combine binary orbital dynamics, colliding wind physics, and radiative transfer through the enveloping gas help to interpret these observations and to place constraints on the companion's effective temperature, luminosity, and wind parameters, even if exact values remain uncertain. The companion's presence has shaped the evolution of the inner nebula over long timescales. As it orbits within the dense outflow from the primary, its wind and radiation sculpt cavities and ionization structures that become part of the broader morphology of the inner ejecta and shells. The spiral-like pattern of shocked gas and ionized zones that trails behind the companion's motion leaves a record of the orbital history imprinted on the surrounding material. Over many orbital cycles, this repeated interaction can carve preferred channels for gas and radiation influence where dust can survive and contribute to asymmetries in the inner structures. Because the orbit is not circular, the strength and character of this influence change from cycle to cycle as the system evolves. Despite the challenges in directly observing the companion, the cumulative evidence from ionization patterns, colliding wind emission, and spectral variability points to a hot massive star whose fast thinner wind and intense high-energy radiation field play a central role in the present configuration of the inner environment around Eta Carinae coexisting with and interacting with the primary's dense wind inside the nested shells of the homunculus and little homunculus. Historical observations of Eta Carinae reveal that the system has not always appeared as it does today. In the early part of the 19th century, it is known as a bright star in the southern sky, but not exceptional among the very brightest. Over several decades, its brightness begins to change. Records from that period describe a gradual increase in luminosity in the early 1800s, followed by a more dramatic rise in the 1830s and 1840s. During the peak of what is now called the Great Eruption, Eta Carinae rivals the most luminous stars in the night sky and becomes visible even in daylight under favourable conditions. This bright phase lasts for years, not days, and marks the event in which the main mass of the Homunculus Nebula is expelled. The light curve, which is a record of brightness over time, shows that the eruption is not a single brief flash, but a complex episode with multiple peaks and intervals of slower change. In the early stages, the star brightens and fades on timescales of months to years. Later, during the main maximum around the middle of the 19th century, it maintains an unusually high luminosity for an extended period before gradually declining. This behaviour resembles that of a supernova imposter, a term used for eruptive events in which a massive star becomes temporarily as bright as or nearly as bright as a true supernova, but does not undergo complete destruction. The Great Eruption of Eta Carinae ejects several solar masses of material into space, forming the bipolar lobes of the homunculus and associated equatorial structures described earlier. The kinetic energy of this outflow is large, though lower than that of a typical core collapse supernova. The exact physical mechanism driving the eruption remains uncertain. Proposed explanations involve combinations of increased radiation pressure in the star's envelope, possible instabilities deep in the interior, and interactions within the binary system, but available data do not yet single out a unique cause. Observationally, what is clear is that the star sheds a substantial fraction of its outer layers over a period of years to decades, and that this mass loss reshapes both the star and its environment. After the main peak, the brightness of Eta Carinae fades, but it does not return immediately to a quiescent state. In the latter part of the 19th century, the system experiences a lesser outburst, during which its luminosity again increases, though not to the extreme levels of the Great Eruption. This event in the 1890s is associated with the formation of the little homunculus, the smaller, slower bipolar nebula nested inside the main lobes. The timing inferred from expansion velocities and current positions of the little homunculus matches the historical records of this secondary brightening. As with the Great Eruption, the detailed trigger for the lesser event is not firmly established, but it demonstrates that the system remains unstable for decades after the major mass loss episode, with additional material expelled in a more modest but still significant eruption. Following the lesser outburst, Eta Carinae's visual brightness declines further, and for much of the 20th century it remains relatively faint in visible light compared with its 19th century peak, though still luminous in absolute terms. During this period, dust formed in the expelled material, and in the dense wind of the primary star plays a major role in shaping the observed appearance. Dust grains absorb and scatter visible light, reducing the brightness seen from Earth, while re-radiating energy in the infrared. As a result, the system's total energy output remains high, but a larger fraction emerges at longer wavelengths. Observations in the infrared begin to reveal the thermal emission from the homunculus dust, and help to quantify the mass of material involved in the eruptions. Spectroscopic studies also show evidence of strong winds and processed material, indicating that the star has not returned to an unevolved state, but continues to experience heavy mass loss. Over the latter half of the 20th century and into the present century, Eta Carinae shows a gradual long-term brightening in visible light. This increase does not reach the extraordinary levels of the Great Eruption, but is significant when tracked over decades. One plausible contribution to this brightening is a change in the amount or distribution of dust along the line of sight. As dust grains are destroyed, redistributed, or become less effective at blocking light in certain directions, more of the star's intrinsic luminosity can reach observers. Another contribution may come from changes in the star's wind properties and outer layers, which alter the emergent spectrum. The detailed balance between these effects is still a subject of active study, but the trend indicates that the system is not static. Superposed on the long-term evolution are variations tied to the 5.5-year orbital cycle, seen in changes in emission lines, X-ray flux, and other diagnostics described earlier. This combination of secular evolution and periodic behavior complicates the interpretation of any single observing epoch and highlights the importance of long-term monitoring. The historical record of Eta Carinae has also been extended by the study of light echoes, which are reflections of past light from the eruptions off distant dust clouds. Because light scattered by dust takes a longer path to reach Earth than light coming directly from the star, these echoes arrive years to more than a century after the original event. Observations of light echoes from the Great Eruption allow spectra of the historical outburst to be obtained long after it occurred, providing additional constraints on the temperature and outflow properties of the star during that time. These data suggest that the eruption involves a very dense cool outflow, rather than the extremely hot fast ejecta, typical of some supernova, consistent with the picture of a massive radiation-driven event, rather than a terminal explosion. Together, the direct historical observations, modern multi-wavelength monitoring and light echo studies build a layered view of Eta Carinae's eruptive history, a gradual rise and extreme brightening in the 19th century, associated with massive mass loss and formation of the homunculus, a lesser outburst a few decades later, linked to the little homunculus, a subsequent period of relative visual faintness, dominated by dust absorption, and a more recent slow brightening and spectral evolution, as the system continues to adjust after these large-scale changes, all within the broader context of ongoing winds and binary interactions that shape the present-day nebula. In its present state, Eta Carinae stands as a massive luminous and still evolving binary system, enclosed within a layered nebula that records centuries of intense mass loss. Observations across the spectrum place the primary star among the most luminous known in the Milky Way, with a mass likely of order many tens to perhaps more than 100 times the mass of the Sun, and a luminosity of several million times solar. The companion star also appears to be very massive and hot, with a mass of several tens of solar masses and a strong radiation field, though its exact properties remain less certain, because it is partly hidden by the primary's bright wind and surrounding ejecta. Together, these stars radiate enough energy to shape the ionization and dynamics of a region spanning many light years. At the same time, their past eruptions and ongoing winds have removed a substantial amount of mass, changing the structure of the primary's outer layers and altering the balance between gravity and radiation in its envelope. The Homunculus Nebula alone contains several solar masses of gas and dust, and additional mass resides in the little homunculus inner ejecta and outer debris. Estimates of the total mass lost in the 19th century events and in earlier and later winds vary, but all indicate that the system has shed a significant fraction of its original mass. This mass loss has consequences for the star's internal structure rotation and future evolution, but the precise state of the core and deep layers is not directly observable and must be inferred from models constrained by current luminosity, temperature, and mass loss behavior. At present, the primary star continues to drive a dense wind, and the colliding wind region with the companion remains a strong source of variable X-ray emission. The 5.5-year orbital cycle repeats with periastron passages marked by changes in X-rays, emission lines, and ionization patterns in the surrounding gas. The long-term brightening seen in visible light over recent decades suggests that the system is adjusting after its major eruptions, possibly through changes in dust distribution, wind density, or the structure of the photospheric layers. However, the underlying causes of this gradual evolution are not yet fully understood. Measurements of the star's effective temperature, luminosity, and wind properties involve complex modeling of radiative transfer in an extended clumped outflow and are subject to uncertainties in geometry and composition. Different models can reproduce some observed features while differing in details such as the current mass of the primary, the precise location of the photosphere, and the role of rotation. These uncertainties make it challenging to place Eta Carinae at a unique position on theoretical diagrams of stellar evolution, although it clearly occupies a regime of high luminosity and strong mass loss, characteristic of luminous blue variables and very massive post-main sequence stars. The stability of the system is an open question. The 19th century Great Eruption and the later lesser outbursts show that Eta Carinae can undergo dramatic episodes in which its luminosity and mass loss rate increase by large factors over relatively short timescales. Whether similar events will occur again is unknown. Current observations show variability in the wind and outer layers, but nothing on the scale of the historical eruptions in modern times. Some theoretical scenarios suggest that very massive stars near the upper limits of stability may experience recurrent outbursts as internal energy transport, nuclear burning, and envelope structure interact in complex ways. Others emphasize the role of binary interaction, including tidal forces at periastron and possible past mass transfer or common envelope phases in driving large eruptions. In the case of Eta Carinae, the presence of a massive companion in a highly eccentric orbit clearly influences the inner environment, but the degree to which binary interaction directly triggered the past eruptions remains debated. Another major uncertainty concerns the ultimate fate of the system. Given its high mass and evolved state, Eta Carinae is widely expected to end in some form of core collapse event, such as a supernova or related type of explosion, but the timescale to that endpoint is not constrained by current observations. Stellar evolution models of very massive stars, particularly those with strong mass loss and binarity, involve uncertainties in how mass loss rates change with time, how mixing operates in the interior, and how rotation and magnetic fields modify the sequence of burning stages. These uncertainties broaden the range of possible outcomes and timescales. Observationally, There is no direct sign that core collapse is imminent. The star remains intact with the dense wind and an irregular but stable orbital cycle, and the nebula continues to expand without obvious new large-scale eruptions on the scale of the 19th century events. The system therefore provides a snapshot of a massive star in a highly mass-losing post-eruption phase, rather than a clear pre-explosion state. Current and future observations aim to tighten constraints on key parameters. High spatial resolution imaging and spectroscopy attempt to map the three-dimensional structure of the nebula and inner ejecta in increasing detail, refining mass and velocity estimates. Monitoring of X-ray emission across multiple orbital cycles seeks to track changes in the colliding wind region and to determine whether wind properties such as mass loss rates and speeds evolve over timescales of decades. Ultraviolet and optical spectroscopy probe the composition and ionization states of the wind and surrounding gas testing models of the primary and companion. Infrared observations measure dust emission and follow how dust is destroyed, reshaped, or newly formed in different zones. Light echo studies add information about past eruptions, potentially revealing whether the 19th century behavior was singular or part of a longer pattern. Despite these efforts, several questions remain unresolved. The exact masses of both stars and the detailed structure of the primary's core and envelope are not directly measurable. The mechanism that powered the Great Eruption, including the relative contributions of internal instabilities and binary interaction, remains under discussion. The degree to which mass losses altered the possible future evolutionary paths of both stars is uncertain, especially given the complex feedback between wind's rotation and internal mixing. Even the total mass and energy contained in the homunculus and related ejecta carry uncertainties due to assumptions about dust properties, gas-to-dust ratios, and geometry. Nevertheless, a broad picture emerges in which Eta Carinae is recognized as an extreme, unstable, very massive binary system that has already experienced at least 2 major eruptions, continues to lose mass through strong winds, and remains embedded in a structured nebula built from its own history of outflows. In this view, the present configuration of the system is a transitional phase in the life of a very massive star marked by ongoing adjustment to past large-scale mass loss, and by continuing interaction between the two stars and the ejecta. They have produced under conditions that make precise long-term predictions difficult and leave the ultimate trajectory within massive star evolution an open, actively studied question.